In this video, we would be treating solubility product constant, Ksp. The following are the topics under Ksp. Writing Ksp expression, calculation of Ksp when molar solubility is given, and vice versa. First topic, solubility product constant, Ksp, and its expression.
We want to discuss solubility product constant now and then proceed to give us what we need to know about Ksp. Now, solubility product constant has a symbol or an acronym, which is Ksp. So anytime you see Ksp, or anytime you're asked to solve for Ksp, you're basically referring to solubility product constant, okay? So we said, if you could recall, when I was treating equilibrium, chemical equilibrium, right, I actually treated with us how to write equilibrium constant expression. And I could remember I said that anytime a reaction is in equilibrium, anytime you see that reversible sign, all right, there's always bound to be equilibrium constant for such reaction. All right, and I also went ahead to say that for only species in equilibrium reaction that are in a gaseous state or aqueous state can appear in equilibrium constant expression. That is in terms of concentration, the Kc, right? For Kp, I said it's only substance that are in a gaseous form that will appear in the equilibrium constant expression. Now we have a new form of equilibrium constant, which is called solubility product constant, Ksp. Now Ksp is mostly written for a sparingly soluble salts, right? When they say sparingly soluble salts, these are salts that do not dissolve very well in water. Some part of it dissolves and some part of it do not dissolve. All right. So for those type of salts, we're going to be writing their solubility product. Right. For something to actually partially dissolve in water, it simply means that there will be an equilibrium between what has dissolved and what has not dissolved. Okay. So let's say, for example, the most common, let's say, for example, we have a salt. Do not forget from our elementary chemistry, a salt is formed when the hydrogen ion of an acid, a normal salt, when the hydrogen ion of an acid is replaced with a metal. For example, we have our HCl. When you replace this H with a metal, sodium, this becomes NaCl. When you replace it with silver, this becomes AgCl. So we said a normal salt is actually formed when the hydrogen ion of an acid is replaced with a metal. So once you see something like this is a salt, all right? Most of the time, they could give you a compound and you're asked to write the Ksp. So once they give you that compound, just assume that this guy is sparingly soluble. In other words, if you dissolve it in water, it's not going to dissolve very well. So this becomes this is a solid. Now, I want to dissociate this guy, right? This is actually a dissociation reaction. In the case of chemical equilibrium, it was more or less like a chemical reaction, two things coming together to give a product. But here, we are dissociating this guy, right? If you dissolve this solid in water, this is solid because it shows it's a solid, like your table salt. If you dissolve this in water, these this substance, these elements will split and become their respective ions. So this becomes Ag plus Cl minus. So the next thing you're going to do is to balance to see if the equation is balanced. So silver is 1 here, silver is 1, so it's balanced. Chlorine is 1, chlorine is 1, so this equation is balanced. So we'll now say this is aqueous. Please take note of that. Any substance that has a plus or a minus on top of it has to be aqueous because you can only have this plus when you're dissolved in water. So my Ksp here becomes equals to, recall, in the case of Kc, we said the ratio to that of the product to that of the reactant. But this time around, the reactant is a solid, right? That is why we are not going to include a reactant. Recall I said, for you to write equilibrium constant, that substance has to be gas or aqueous. Gas or aqueous. So this is an aqueous, so we can actually write for this. But this is a solid, so we are going to ignore it. All right, so this becomes So this is how we write Ksp for this salt. So like I said, from the topics I gave us, the first topic is that you need to know how to write Ksp expression for different salts. You need to perfect your understanding on how to write Ksp, because if you don't really know how to write this expression, you won't be able to solve or carry out calculation under this topic, because everything is tied to this. Okay, so what if I proceed to give us II, Pb, Cl2. All right, so now we have 4 examples here. Please pay attention. Now, for you to be able to know how to write Ksp expression, that is this, you must know how to dissociate and give the correct product for each of the salts. Because if you don't really know the product of this, how would you be able to write the correct expression for this? So just pay attention. Let me guide us on how to identify or how to write the correct product for each of these salts. Now, first thing first, a salt is always made up of 2 components. All right, the positive components and the negative components. Salts are ionic compounds. All right, so ionic compounds must always have a negative terminal and a positive terminal. All right, so the positive terminal is always a metal. Right, the one that will be the positive charge is always a metal. In other words, metals will be the ones that are written first. So metals are always written first. So I'm just giving you this in case maybe before now you don't really know which is metal and which is non-metal. So anytime you're being given a compound and you're asked to write the Ksp, just remember this, that Ksp is written for mostly salts, and salts are ionic. Ionic means it has a positive end and it has a negative end. The positive end is always the metals. The negative ends are always the non-metals. All right, point number 1. Number 2, the positive ends are the ones that are always written first. Like in this case, the one that is written first, Ag, silver, Ag stands for silver, is a metal. Pb stands for lead, is a metal. Silver is a metal. Magnesium is a metal. Barium is a metal. Now, once you've written the first one out, every other thing becomes the non-metal, right? The non-metal or the anions, let me say the negative components. The negative component, it can be a single atom or it can be a combination of atoms. In this case, this Ag, once you've written the Ag, every other thing that was attached to this Ag have to make up the other side. Do you understand? So now let's look at this. So I'll say this is a solid. So this is solid. So when you write this, the first thing you're going to do, let's start. I know a lot of us may not really know the charges of the metals before now, right? So I'm going to help you guys out. So first thing first, the metal component is a Pb, the one that is always written first, please. So I'll say Pb plus every other thing that is attached to this, Cl. Now, you ask yourself, how many of these Cl do we have here? Is 2. Class, take note of what I'm about to say now. Pb has a charge of +2. And Cl has a charge of -1. So this is what I'm going to do, right? Now, I'm going to actually, after now, write out most of the metals you're most likely going to see whenever you're solving for Ksp, and I'll write out most of the anions. Anions are the negative charge. The metals are the cations. So I'm going to write out the positive, which are the cations, the possible metals and their charges, and I'll write out the anions and their charges as well, so that you take note of them, right? So you don't have to start, oh, how will I know this? Don't bother yourself. Now, Pb is always 2 plus and this guy is always minus. Please endeavor to balance the equation. So if there is an atom, if there's a number here, please check if it is balanced. If I did not add these 2, this is not balanced. Chlorine here is 2, but chlorine here is 1. So I need to balance this guy. Okay, the next thing I'm going to do, please ensure you add aqueous here. So once you do that, my Ksp for this now becomes Ksp equals to the concentration of this product raised to their coefficient. Class, remember, we're not going to do divided by the reactant, because this reactant is a solid, and solid do not take part in equilibrium constant expression. So this becomes Pb 2 plus, and do not forget, we are going to raise this by their coefficients. Okay, now this second one goes as follows. Now Ag, the first element is Ag plus, please, once you've written Ag, like I said, once you've written the first the metal, every other thing are together. So don't come and say S. No, don't do that. Once you've written the first component, which is a positive component, every other thing becomes together, SO4. Okay, so let's balance this guy. Ag is 2 here, you come here and you put 2 here, SO4 is 1 here, SO4 is 1. The next thing you're going to do is that, what is the charge of silver? Please, the charge of silver is plus. What is the charge of SO4? Is always 2 minus. Do not forget, I said I'm going to be giving us, after now, I'll give us all the anions and all the cations, so they take note of the charges of the metals and also that of the non-metals. Okay, so I'll check. Silver is 2 here, silver is 2, SO4, SO4. So the next thing I'm going to do here is to add aqueous. I add aqueous. So therefore, my Ksp for this guy becomes Ag plus, raise to the power of 2. You need to raise it to the coefficient, into this. Can you see that? All right. So the next thing here, so Mg, one side. Mg is one side. So this is a positive component. So you come here, you say Mg plus everything, apart every other thing is together, right? So thank goodness that PO4 is inside a bracket. So this becomes PO4. Thank God that this is inside bracket. So it makes it very easy. But even if it was inside, even if it was not inside a bracket, once we've gotten the first part, every other part is actually together. So once you've done this, the next thing you're going to do is to balance. Magnesium is how many here? 3. So I'll come here. I'll say, I'll put 3 here. PO4 is how many here? 2. Now the charge of magnesium is always 2 plus, and the charge of PO4 is always 3 minus. I know a lot of persons will be like, how will I know that this thing is 2 plus? Well, it's not in this particular topic I'm going to teach that. If I do that, we are going to deviate so much. So there is a video dedicated for this already. So the next thing you're going to do is to add aqueous. So this becomes, my Ksp becomes equals to you raise it to 3. PO4 is 3 minus. The coefficient is 2. So we have written that for magnesium phosphate. This is magnesium phosphate, silver sulfate, lead chloride, and barium sulfate. So the next one is going to be barium. Class, barium is basically a metal. So we say Ba plus SO4. Barium is 1 here, SO4 is 1 here. So in terms of, atoms, they are balanced. So we start adding their charge. Barium is 2 plus. This is 2 minus. You come here, you add aqueous. You come here, you add aqueous. So therefore, our Ksp becomes barium 2 plus inside brackets. The coefficient is 1. So raising this guy to 1 is equivalent to not raising it to anything. So this becomes SO4. So guys, you can see how we are breaking our Ksp for the various salts that we have here. Just like I said, I would be giving us the metals, the possible metals you're likely going to see when solving for Ksp, and the possible non-metals and the anions. All right. So please make sure you actually go through them, jot it somewhere inside your notes so that you don't actually forget them. All right.
Okay, so this is basically the metals and the non-metals, right? So you need to take note of these charges, right? So take note of the
Next topic, calculation of Ksp when molar solubility is given.
Right, guys, we are done with the first part of Ksp was knowing how to write the expression, just like I told us. So the next one now is for us to actually carry out calculation of Ksp when molar solubility is given. Now, molar solubility, this place I can also call it molar concentration, right? So you may be asked to solve for the Ksp, that's the solubility product constant, for a particular salt. It could be AgBr, it could be AgI, right? Now, they will give us the molar concentration, which in other words is also known as molar solubility, right? So if you are being given molar solubility, it must always be in molar concentration, like in molar, right? So note the units of the solubility or concentration must be in moles per liter, which is same thing as saying mole per dm cube, which in simple term is always written as m. That is molar. Class, if they give you a concentration or a solubility and the unit is not in mole per liters or mole per dm cube or just as m, it simply means that that concentration or that solubility is not molar concentration or molar solubility, right? And if the concentration is not molar, right, you cannot substitute into the equilibrium constant expression. Remember, in equilibrium constant expression, we use a square bracket. This square bracket denotes molar concentration. So for anything to be found inside of this square bracket, that must be in molar. So this is molarity. Molarity, molar concentration, molar solubility, they are all the same thing. Right? So imagine in a case where you're being given a question and the concentration is not given to us in molar, mole per liters or mole per dm cube, we have to carry out conversion to convert it to molarity, which is mole per liters or mole per dm cube. All right, so please take note of this. So now this particular question here, the unit of the concentration is already in molar. So there will be no need for us to carry out any conversion. So we just proceed with our solving. Now the first thing you're going to do for you to get this answer is to first write equilibrium expression for that. So I'll say solution AgBr. This is a solid. If this you dissociate in water, we're going to have Ag. Ag is always plus and Br is always minus because Br and Cl, they belong to the same group. So their charges are the same. Okay, so I'll come down here and say this is aqueous and this is aqueous. Okay, please look up. The next thing we are going to do is to say the concentration that they gave to us was for that of AgBr. They said calculate the Ksp for AgBr solution of this. So that means this 8.8 times 10 to the power minus 7 is for this AgBr. But before we proceed, the mole ratio of this is 1 is to 1 is to 1, which simply means that 1 molar of this will give us 1 molar of this, and this will always give us 1 molar of this. So I will now say, so since they gave us here to be 8.8 times 10 raised to the power minus 7, and since their ratio is 1 is to 1, because the coefficient here is 1, the coefficient here is 1, and the coefficient is always 1. So 1 molar of this is equivalent to 1 molar of this, which is something like this. So if I have 8.8 times 10 raised to the power minus 7, here will also be 8.8 times 10 raised to the power minus 7. Here will also be 8 times 8 times 10 raised to the power of minus 7. So therefore, I'll now say Ksp will be Ag, this raised to the power of 1, but I'm not going to write it since it is 1. We have Br minus raised to the power of 1, but since it is 1, I'll leave it out. So this is equivalent to saying 8.8 times 10 raised to the power of 7 times 8.8 times 10 raised to the power of 7. All right, so basically, the concentration of silver ion is going to be this, because since the ratio is 1:1, whatever the concentration of this guy is will be the same as that of Ag plus, because their ratio is 1:1. All right, same thing as Br minus, because the ratio is 1:1. Okay, so when you actually carry out this now becomes equals to, we have 7.74 times 10 raised to the power of 13. Can you see that? As simple as that. Now, some persons are asking me, or some persons might ask, is this stuff, does it have a unit? Well, yes, it can have a unit actually. It's the unit is derived, can be derived. So if you look at this is concentration. Okay, so if I say Ag plus and Br minus, this is concentration, we'll say molar. This molar is raised to the power of 1. This is another molar raised to the power of 1. So this is molar squared. So if you're asking in terms of the units, this would be molar squared. But most of the times they don't usually, ask for the units. So that is how we got the answer for that question. Now let's look at another question. So we have another question here that says calculate the Ksp of Ag2CO3 whose molar solubility is 1.2 times 10 to the power of minus 4 molar. All right, so it's very simple. You're asked to find the Ksp of this. All right, so how do we go about it? Class, look up. I'll say solution. If you noticed, the unit of this guy is already molar. That was why they said molar solubility. All right, so if this stuff was not in molar, they wouldn't have said molar solubility. They would have just said solubility or concentration. All right, that does not mean once you see molar solubility, you should just start solving without confirming if the unit is molar. Okay, all right, so first thing first, you need to write equilibrium expression for this, which is going to be Ag2CO3 solid Ag plus 2 moles plus this is aqueous. This is aqueous. If you look at the mole ratio, this is 1:2:1. All right. So you now say whatever the concentration of this guy is, which is what they gave us in that question, they said AgCO3, the molar solubility. Please, molar solubility is the same thing as saying molar concentration. I told you guys here. So if they use molar solubility, it's equivalent to say molar concentration. So if this is 1 here, this is 2, this will also be 1. So we say 1.27 times 10 raised to the power of minus 4. And this guy would be 2 into 1.27 times 10 raised to the power of minus 4. And this guy would be 1.27 times 10 raised to the power of minus 4. Now, if you press your calculator, this should be 2.54. Yeah? So this is 2.54 times 10 raised to the power of minus 4. So therefore, your Ksp will now be, you write Ksp expression for this, it will be Ag plus squared raised to the power of 2 CO3 2 minus raised to the power of 1. All right, so anywhere you see concentration of Ag plus, recall Ag plus is 2 moles to this. So whatever the concentration of this guy is, we're going to times it by 2. And when we did that, this was what we got. So in place of this silver, you're going to put 2.54 times 10 raised to the power of 4. Please, you must also raise it to 2. So in case some persons will say, but why will I raise it to 2 since I already multiplied? Now, what you just did here is the concentration of this. It has no business with this squared here. So this squared is actually obtained by writing equilibrium constant expression for this, the Ksp for this. So this squared is as a result of this Ksp. So it has no business with this concentration. What you multiplied here is simple stoichiometry. This is 2 and this is 1. So whatever this is, this place will be times 2 of it. So if here is 1.27, here will be 2.54. So it has nothing to do with these two. So you must raise it to this 2. You know, Tago? Now CO3 is 1:1. So whatever the concentration of this guy is, it will be this. So we have 1.27 times 10 raised to the power of 4. All right, so therefore, our Ksp will now be equals to 8.19 times 10 raised to the power of 12. Now, in case you're wondering, how can we actually attach units to this? Now, this is molar. This is molar, right? This square bracket stands for molar, but there's a square here. So this is more like saying molar square from this and molar here. This is raised to the power of 1. So 2 in indices, if the base are multiplying, you add the powers. So 2 plus 1, so this becomes 3. So this becomes the Ksp for this. Now, so we have done 2 calculations using direct unit of concentration of molar. But do not forget that all questions must not necessarily come as this. So what if in a case where they give us concentration or solubility not in molar, but maybe in grams per liters or in any other unit apart from molar? How do we solve it? Well, stay tuned and see how we're going to unravel the solving. Okay, we have another question here. Now this time around, remember I told us that what if you are asked to solve for the Ksp and then the solubility or the concentration is not given to us in terms of mole per dm cube or mole per liters, which is equivalent to saying molar. How do we go about it? Now we have a typical example here. We said a saturated solution of AgCl contains 1.46 times 10 to the power minus 3 grams per dm cube at 108 degrees Celsius. Now they say, what is the Ksp of AgCl at this time? Now, if you look at this question very well, you're going to realize that the solubility or the concentration, I'll say solution, concentration is not the concentration is not molar concentration. And remember what I told us, that if it is not molar concentration, you cannot solve for the Ksp, because the Ksp would actually need its concentration to be in molar, so that when you substitute into the expression for Ksp, it will actually, be evaluated properly. So first thing first, I'll say first, convert grams per dm cube that's molar. That's the first thing you're going to do. And what is the relationship? I'll say molar concentration is equals to mass concentration plus. The same way, molar concentration has a unit of grams. Molar concentration has a unit of mole per dm cube or mole per liters. Gram concentration, mass concentration mass concentration can be in any form. It can be milligrams per liter. Milligrams is still a grams, all right? But the right unit for mass concentration is always grams per liter. So if you look at this, this is grams per liter. There is a relationship between, please, dm cube and liters are the same, all right? So in case we interchange them, all right, or in case it is being used interchangeably, the relationship between mass concentration, that is grams per dm cube or grams per liter, to molar concentration is this formula. Molar concentration is mass concentration all over molar mass, right? So the molar mass of this particular compound, AgCl, is already given to us. That makes it very easy. Okay, in a case whereby it's not given to us, I think they should actually give us the atomic mass to sum up together to get the molar mass. So this becomes mass concentration of this guy is 1.46 times 10 raised to the power of 3 grams per dm cube all over the molar mass of AgCl from the question is 143.5 grams per mole. So therefore, molar concentration is equals to, when you carry out this evaluation, if you carry out this evaluation, what are we going to get? This is what we are going to get. So we're going to get the molar concentration. So therefore, AgCl square brackets please, this square bracket stands for concentration. So it's equivalent to me saying concentration of AgCl. All right. I will now say AgCl, when this dissociates, we're going to have Ag plus Cl minus. This is aqueous. So this is 1:1:1, which means whatever the concentration of this AgCl is, which of course is this, since the ratio of this guy, please, how do we get this 1:1? If you look at the coefficient of AgCl, it is 1 here. Coefficient of Ag plus, it is 1. Coefficient of Cl minus, it is 1. Right? So this is the ratio of this is 1:1:1. That means the concentration of AgCl will be the same concentration as that of Ag plus, and will be the same thing as that of Cl minus. Right? So it's actually safe for us to say that the concentration of Ag plus will be 1.02 times 10 raised to the power of minus 5. And that of Cl minus will also be the same. Why? Because their ratio is 1:1. So I'll therefore say, so therefore, Ksp of AgCl would be Ag plus Cl minus. So anywhere you see Ag plus, you're going to put 1.02 times 10 raised to the power of 5 into 1.02 times 10. So when you press your calculator, times 10 raised to the power of 10. And once again, just in case you want to add the units, this is molar raised to the power of 1. Molar, this is also molar. So molar times molar to give us molar squared. So that is how we got the answer for this. So this is the Ksp for this class. Let me say this. What if in a case where this is gram mass concentration? Remember I said mass concentration simply means the unit is in mass and in volume, right? But anytime we talk about mass concentration and you want to use this formula, class, the formula that relates mass concentration to molar concentration is this. Molar concentration or molarity is mass concentration all over molar mass, right? So this guy has to be in grams per liters or dm cube, and this guy has to be mole per liters or dm cube. Now, what if they had given us the volume in milliliters? Class, remember, here being dm cube is equivalent to here being liters. So if they give us the volume in liters, right? Imagine this guy, they now convert here, they now say here is now milliliters, just assuming. Class, you cannot use this value in this formula. No, this formula here, for you to use this formula, this place has to be grams per liters. So first thing first, you need to convert this mil to liters first. So once you convert this mil to liters, you can now have grams per liters. From there, you can now substitute this value into the mass concentration. All right. Okay. Now let's look at the next question. The question says, analysis of PbI2, that's lead iodide, showed at 25 degrees Celsius that 0.25 dm cube of the solution contains 0.141 grams PbI2. Calculate the Ksp for PbI2. This time around, they actually gave us the mass and they gave us the volume. So it is left for us to construct, and get the molarity of that compound. So I'll say solution. Now, first, solve for molarity of PbI2. Now, if you look at this, they gave us the volume and they gave us mass. So this is what I would do. I'll say molarity. There's a relationship between molarity and volume. So this is molarity equals to mole all over volume. But if you notice, they did not give us the mole of PbI2. What they gave to us was the mass of PbI2, right? And then they gave us the molar mass of this. The volume is already in dm cube, which is actually the normal unit of volume that we need. So class, remember that mole is same thing as saying mass all over molar mass. So this is equivalent to writing mole times 1 all over V. Class, I want to actually show something. Mole over liters, mole over volume is equivalent to say mole times 1 all over volume. So that I want to replace this mole with mass all over molar mass so that it will be very easy for us. So this now becomes, in place of mole, I'll say mass all over molar mass times 1 all over volume. Now, what is the mass of PbI2? 0.141 grams. The molar mass of PbI2 was given to us already. So this is 461 grams per mole times 1 over volume. This is equivalent to saying 1 all over. The volume given to us is 0.25 dm cube. Class, grams will cancel grams. This is per mole, which is equivalent to saying when per moles comes up, it now becomes mole. So the molarity of PbI2 will now be, when you carry out this evaluation, this becomes equals to 1.22 times 10 raised to the power of minus 3 molar. Class, what we are solving now is molarity. This is same thing as saying mole per dm cube. This is equivalent to say mole per dm cube, which is the same thing as molar. All right. Now, we have gotten the concentration of PbI2. What is left for us to do now is to actually get the Ksp for this. And remember, once you've gotten the molar concentration or the molar solubility of the salt in question, right, you can always get your Ksp. So I'll say PbI2 is a solid. So this becomes Pb2 plus aqueous plus, I already taught us how to write an expression for this. So our Ksp, this becomes 1:1:2. Now, if you look at the ratios here, this is 1 mole, this is 1 mole, and this is 2 moles. All right, so when you do that, whatever the concentration of this guy is, will be the same thing as here, but in this case, it will be times 2 of whatever the concentration of this guy is. So we say this is 1.22 times 10 raised to the power of minus 3. That is the concentration of this. This guy is 1.22 times 10 raised to the power of minus 3. And this guy is 2 into 1.22 times 10 raised to the power of minus 3. And when you do that, this is 2.44 times 10 raised to the power of minus 3. So therefore, my Ksp is equals to Pb2 plus recipe of 1 into recipe of 2. Alright? So anywhere I see Pb2 plus, I'll put 1.22 times 10 recipe of 3. Anytime I put this, I'll become 2.44 times 10 recipe of minus 3. Remember, you have to always square it. If here was recipe of 2, you have to raise it. Irrespective of the fact that you had earlier multiplied this guy by this coefficient, right? What we just did here was to get the concentration of I. This 2 has no business with this. This 2 is because you wrote equilibrium solubility product constant of this. So when you carry out this calculation, this becomes 7.26 times 10 raised to the power of 9. Now, just in case you want to add the units, this is molar raised to the power of 1. This is molar squared. So molar squared times molar is molar cube. Okay, so guys, we've actually solved 4 examples under calculation of Ksp when molar solubility or solubility in different units, or perhaps they just give you mass and volume. We've seen how we got the answers for that. So I believe with these 4 examples, if you understand them very well, right, honestly, there's no question under this section you won't be able to solve. So we're going to be solving last section under Ksp, and then we bring Ksp to an end. And what is that section, class? It's just the opposite of what we did here. In this case, right, they will give us molar solubility, or they will give us molar concentration, and you'll be asked to solve for the Ksp. In the next session, on the next episode that we're going to be treating, they will give you the Ksp, and you're going to be asked to solve for the molar concentration. So it's opposite. The one we just completed now, they gave us molar concentration, right? And we are asked to find the Ksp, and we got the Ksp. So the next video we're going to be making, or we're going to be shooting, would be to solve for molar solubility when Ksp is given, right?
Next, calculation of molar solubility when Ksp is given.
Calculation of molar solubility when Ksp is given. Remember, like I said, this particular topic is the opposite of what we did previously. Now, in the previous case, it was calculation of Ksp when molar solubility is given. So here it's more like the reverse of the first one. Now, if you look at, we have 3 questions here. At the end of these 3 questions, I believe you should actually, get the concepts behind this. You don't have to solve hundreds of questions to be able to grab this perfectly. They said the first one says, calculate the molar solubility of PbCl, lead chloride, given that the Ksp of PbCl is this. So I'll start with the first one. I'll say solution question 1. Please pay attention. Right. Now they said, we'll say let's molar solubility of PbCl2, which is, let's call it X. Now this square bracket stands for molar solubility. Let's call it X, right? I'll now say, write equilibrium expression for this. Now this is Pb2 plus, this is Cl minus 2. Now first thing first, we do not know the concentration of this guy, alright? In the previous case, when they gave us the molar solubility or the molar concentration, we said this is 1:1:2. So whatever the concentration of this guy is, it will be the same concentration as that of this guy. But right now, we do not know the value or the concentration of PbCl2, right? We had earlier made it to be X. So I will say, if here is 1:1:2. So since we said let the molar solubility of this guy equals to X, if here is X, here will also be X, since both of them are 1:1, and here will be 2X, since this is 2. So all I just need to do now is to solve for my X. Whatever the value of X is, that becomes the molar solubility of PbCl2. How do we solve for X? Follow me. So I'll say, so therefore, Ksp becomes Pb2 plus raised to the power of 1 times Cl minus raised to the power of 2. Do not forget that this is equals to, they gave us the Ksp of PbCl2 to be equals to this, right? So you're going to equate it to 1.6 times 10 raised to the power of minus 5. Anywhere you see Pb2 plus, you put x. So this is x. Anywhere you see Cl minus, you put 2x. But do not forget, you're going to raise it to 2. And this is equals to 1.6 times 10 raised to the power of minus 5. Now 2x squared is 4x squared. If you multiply this, this becomes 4x cubed, right? So I'm going to 4x cubed. This becomes 1.6 times 10. All right, are you following me? So if you make this guy subject of a formula, this is 1.6 times 10 raised to the power of minus 5. Now making x cubed subject of the formula, we just want x cubed to stand alone. So this is achieved by dividing both sides by 4. If you divide both sides by 4, this 4 will be cancelled by the 4 down, leaving us with this. So we want to just get the value of x alone. Class, if you have x squared, for you to get the value of x, you take the square root of what we have on the other side. If these 3 were to be 2, for us to get the value of the x, we're going to take the square root of what we have on the right hand side. But since here is 3, we are going to take the cube root of whatever we have on the right hand side. So this becomes x equals to cube root. Class, if you're pressing your calculator, if you do this, this is not cube root. Calculator is going to say 3 times square root of whatever you have here. So if you want to get this guy in your calculator, press your shift in your normal calculator, press your shift and then look in your calculator. You're going to see where you have the square root. When you press shift, you're going to see a sign like that looks like this. Press it, you're going to get this. And then take note that cube root, the 3 has to be enclosed with this. So this is 1.6 so the value of x now becomes equals to, now the value of x now becomes equals to this. Do not forget that we had earlier said, let the molar solubility of PbCl2 equals to x. So therefore, we can now say, so therefore, molar solubility of PbCl2 is equals to 1.6 times 10 raised to the power of minus 2 molar. The reason why this is molar because we are solving for molar solubility, which is same as molar concentration. And the unit of molar concentration is molar. All right. So let's solve the next example. So let's look at the next question. Question 2 says the Ksp of calcium hydroxide is 6.5 times 10 raised to the power of minus 6. Calculate the molar solubility or concentration. I intentionally added concentration just in case. But I doubt if they want to use the concentration. They always use molar solubility, or they prefer to use molar solubility since we are talking about solubility products. All right. So I'll say solution. First thing first, right? Calcium hydroxide is CaOH. I'll say let concentration. Class, once you see me enclose a compound with a square bracket, it means or it stands for concentration. So let concentration of this guy is equals to X. All right. So the next thing we're going to do now is, I'll say calcium hydroxide is Ca2 plus OH2. But we do not know the value of this. That is why we made it to be X. So using mole ratio, this is 1, and this is 2. So this becomes 1 is to 1 is to 2. Do you understand? So if here is X, here will also be X. and here will be 2x. Alright, so I'll therefore say Ksp is now this is calcium 2 plus raised to the power of 1 and then times OH minus raised to the power of 2. So anywhere we see Ca2 plus, we put x. So this is x. Anywhere we see OH, we put 2x squared. Now this is equals to, do not forget that you're going to equate this to the Ksp value that they gave to us. Alright, so this is 6.5 times. So this is 6.5. So if you evaluate this, 2x raised to the power of 2 will be 4x squared. 4x squared times x will be 4x cubed equals to 6.5 times 10 raised to the power of minus 6. Okay, so the next thing you're going to do here, if you divide both sides by 4, we want to make x cubed subject of the formula. So we divide both sides by 4, this becomes 6.5 times 10. Please, I would advise not to actually get the result from here before you find the cube root, right? So this is what I mean. If you press 6.5 times 10 to the power of minus 6 or divided by 4, don't write out the answer and then take the cube root of the answer. Whatever the answer gives to you, take the cube root of that answer, or preferably take the cube root of this entire stuff we have here. So x becomes, if I have x cubed and I want to take the cube root, I'll press shift in my calculator, then go to where I have the square root sign, press the square root. Something like this will come up. So this is 6. So when you press your answer, this now becomes 1.2 times 10 this now becomes 1.6 times 10 to the power of minus 2. Please endeavor to confirm this with your calculator, just in case my answer here is wrong, right? Just this, in case this final answer is wrong, endeavor to confirm my final answers with your calculator, all right? So therefore, we now say, concentration of calcium hydroxide, which we had earlier designated as X, is now equals to 1.6 times 10 raised to the power of minus 2 molar. So that is the answer for the second one. Now let's solve the third guy. Now let's solve question 3. Let's solve question 3. Question 3 says, calculate the molar solubility of AgCl of Ksp 1.8 times 10 to the power of minus 10 in water. Class, I use this water so as to explain something to us in details, because after now we're going to look at factors that affect molar solubility, where we're going to be talking about common ion effects and uncommon ion effects. But before then, if you're asked to solve for the molar solubility of a compound in water, class, in water is equivalent to not using the word water. So these two examples we had earlier solved, right? Their molar solubility is equivalent, is in water as well. So if they use in water, you shouldn't actually allow this to bother you. If they use in water, is equivalent to not using in water at all. However, if they mention any other compound other than water, you cannot ignore it. You have to take it into consideration. So if water is mentioned, it's equivalent to not putting water at all, just like we did previously, right? But if any other compound other than water is mentioned, you will not ignore that compound. You have to take it into consideration. We're going to be looking at that example after now. So we have solution. Here we'll say let molar solubility. Please, molar solubility is equivalent to say molar concentration. That is why we have been using this square bracket. It's the same thing. So we'll say molar solubility of AgCl equals to X. So I'll say AgCl, when I write my expression, equilibrium expression, here becomes Ag plus aqueous plus Cl minus aqueous. Now this is 1:1:1, which means if here is X, here will be X, and here will be X, because 1:1:1, their coefficient is 1:1. So I'll now say, so therefore, Ksp is Ag plus times Cl minus, this is equals to the value of Ksp that was given to us, 1.8 times 10 raised to the power of minus 10. So anywhere I see Ag plus, I'll put X. Anywhere I see Cl minus, I'll put X. Now this is equals to 1.8 times 10 raised to the power of minus 10. X times X, X squared, right? So for me to now find X will now be, remember I said when you have X squared, right, you have to take the square root of the other side for you to get your X. So this becomes 1.8 times 10. So when you do that, this now becomes so X is 1.34 times 10 raised to the power of minus 5. So therefore, molar solubility of AgCl, which we had earlier said is X, will now be equals to 1.34 times 10. Okay guys, so we've actually come to the end of the first part of Ksp. The next topic we're going to be talking about, or we're going to be looking out for, is factors that affect molar solubility.
Next, factors affecting solubility of a sparingly soluble salt.
To discuss factors affecting solubility of a sparingly soluble salts. In the previous videos, we actually saw how we can calculate for molar solubility of a sparingly soluble salt when Ksp is given and vice versa. So I also treated with us how to write Ksp expression. So the next one we have here is actually to look out for the factors that affect the solubility of a sparingly soluble salt. Now basically, when we talk about solubility, we are talking about substance being dissolved in water, right? So when you dissolve a substance in water, so water is mostly used as to dissolve most of our solutes. So water is a universal solvent. All right. So what if in a case whereby we now decide to not just use water? In addition to having water, you add something else inside the water. How will it fare? That's basically what we want to talk about here. This is common ion effect. Common ion effect is an effect that arises when common ions are present in a solution. There are effects that arises when common ions are present in a solution. Now, common ion effect decreases or reduces the solubility of a sparingly soluble salt. So let me give us an example. Let's say, for example, we have sparingly soluble salts, AgCl. Right? Now we now told that AgCl was dissolved in NaCl solution. Now this time around is not dissolved in water, right? Water is a normal solvent that we are supposed to use, but in a case where we're no longer using water, we now use a salt solution. Now look at this. When both of them are dissolved, now the sparingly soluble salt obviously will dissociate and give us Ag plus and Cl minus. Now this is a sparingly soluble salt, right? When it comes in contact with a solution, it's going to dissociate. Now do not forget that the solution they said is already NaCl or dissolved in NaCl. So this is NaCl. When this guy splits, we're going to have Na plus and Cl minus. If you look at this, there is a common ion between the sparingly soluble salts and the salts of the solution. So what is a common ion? Both of them, they are ions. Ions could either be a positive charged ion or a negative charged. So this guy has a chloride which is negative, and this guy also have a chloride which is negative. So both of them are common. So this is actually what we mean by common ion, effect that arises when common ions are present in a solution. So remember, two of them, AgCl, was dissolved in NaCl solution. That means both of them are present in the solution, and in the solution, Cl minus are the same. Now, what is the effect of dissolving this guy in NaCl solution? Class, if I had dissolved AgCl in water, there will be no effect, no common ion effect, right? The solubility of that guy will have nothing that will actually impede it. But in a case where this is dissolved in NaCl, because of the presence of this Cl minus that is present in both of them, guys, this will reduce the solubility of this guy. If this AgCl was supposed to dissolve 10 grams in water, because of the presence of this NaCl, let's say it's now going to become 5 grams in NaCl solution. So therefore, the presence of a common ion, class, decreases or reduces the solubility of a sparingly soluble salt. Another example of a common ion, let's say I have, for example, I have barium sulfate. This is a sparingly soluble salt. When this dissociates, you're going to have barium 2 plus SO4 2 minus. When I dissolve, if this is dissolved in a solution of Na2SO4, class, when you dissolve this in a solution of this guy, this is what we're going to have. This is going to be Na plus SO4 2 minus. SO4 2 minus are common. So therefore, the solubility of this guy will reduce in the presence of this guy because there is a common ion between two of them. How about if I have a sparingly soluble salt, AgCl, and we have this dissolved in AgNO3, for example, so that you don't say, is the common ion always a negative? No, it can also be the positive. So this is Ag plus and Cl minus. When you dissociate this guy, this is Ag plus NO3 minus. Guys, can you see that there is a common ion here? Ag plus is common. So therefore, there is a common ion between this and this. So the solubility of this guy will decrease in the presence of this. Class, having said that, please take note of this, that the solubility of a sparingly soluble salt will decrease in the presence of a common ion. I believe that is self-understood. Okay, so they might ask you the presence of common ion dash the solubility of a sparingly soluble salt decreases or reduces. Do you understand? Now let's talk about uncommon ion. Guys, opposite of common is uncommon. So uncommon ion effect is also known as salt effect. So basically, what is salt effect or uncommon ion effect? Now this is an effect that arises when there is a presence of a salt which does not have any common ion with the sparingly soluble salt. So this arises when there is a salt which does not have any common ion with that of the sparingly soluble salt. For example, we have example AgCl dissolved in Na2SO4. So if you actually dissociate AgCl, this is what you're going to have, Ag plus Cl minus. And if you dissociate Na2, this is what you're going to have, Na plus. Guys, these are the ions of the sparingly soluble salts, and these are the ions of the salts, added salts. If you notice, there is nothing common between two of them. Ag plus is not the same as this. This is not the same as this. So you notice that these ions that are present are uncommon with the ions of the sparingly soluble salt. So therefore, the presence of an uncommon ion increases the solubility of a sparingly soluble salt. Now this is opposite of this. Common ion decreases the solubility of a sparingly soluble salt. Uncommon ion increases the solubility of a sparingly soluble salt. This common ion is also known as what? Salt effect. But in exam, do I have to start writing out all of this? No. Right? So once you look at the compound, the sparingly soluble salt, and you look at this compound, if they have something in common, obviously, there is a common ion between them. All right? So take note of this. Uncommon ion increases the solubility of a sparingly soluble salt, whereas common ion decreases it. Now, those effects is what we call the common ion effect and uncommon ion effect. So if I have AgCl, I'll say which of the following will decrease the solubility of AgCl? A, NaCl, B, Na2SO4, C, D, none of the above. The question is, which of the following will decrease the solubility of AgCl? This AgCl is a sparingly soluble salt. Now, for anything to decrease the solubility of this, they must have a common ion with this salt. All right, so I don't really have to start dissociating this. I can simply tell this guy has Ag and Cl. So I'm just going to look through these options. Any one of them that has Ag or Cl will decrease the solubility of this. Anyone that has the same ion as found in this salt will decrease its solubility. So let's start from this. Sodium is not the same, but chlorine is common with this guy. Nothing else is common between this and this. Nothing is common here. Nothing is common here. So the answer to this is this. So NaCl has a common ion with AgCl. So therefore, NaCl will decrease the solubility of AgCl. Right? So we're going to be taking calculation questions to see how this will be done.
Next, calculation involving common ion.
Alright guys, welcome back. We have another question here. This is under common ion effects. Now they said calculate the solubility of PbCl2 in the presence of 0.05 molar NaCl at 25 degrees Celsius. Now this basically what they told us. Now normally they would have asked us to solve when it is dissolved in water. If it is dissolved in water, that's basically the ones we've done before now. But if it is dissolved in any other solvent or in addition to water, there is something else, right? There are patterns in which you are going to follow. So let's start with the first one. I'll say solution. So the first thing you're going to do is to actually write Ksp for the salt. Now, the sparingly soluble salt is PbCl2. So I'll say for the first one, PbCl2, this becomes Pb2 plus Cl minus. All right, so the ratio here is 1 is to 1 is to 2. So we do not know the molar solubility of, we have to solve for the molar solubility of this PbCl2. Remember, anytime they give us Ksp and you're asked to solve for the molar solubility or solubility, I've already shown us how to do that. So I'll say let X equals to the molar solubility or molar concentration of PbCl2. All right, now we do not know the concentration of this or the solubility of this, which is what we are asked to find. Right, we are coming to when it is dissolved in this. So let's first of all understand this trait. So now say the relationship here will now be x 2x based on the mole ratio. If here is 1 and here is 1, this is x is to x. All right, and if this here is 2, that's 2x. Okay, so having done that, the next thing we are going to do here is to simply say when it is dissolved in NaCl. So we'll say when it is dissolved in NaCl, you can choose to use one head arrow or double head arrow. This is Na plus Cl minus. Now this is 1:1:1 class. If you look at these ions, do we have anything common between the ions here and the ions here? Yes. This PbCl2 has Cl minus, which is common with this other Cl minus. So it simply means that whatever the concentration of this Cl minus is, right, is going to add up to the one we are going to find here. So here, the concentration of NaCl is 0.05, 0.05, 0.05, based on 1:1:1. So we actually want to find the concentration of Cl, but bear in mind that since these two Cl here are common, we know the concentration of this guy. We do not know that of this guy. That is why we say 2x, right? So it means that whatever this value is, it will add up to what we have here. It's just like, imagine you have sand and nails inside a container, and you now come and pour nails inside the container, right? The nails will actually add up to the nails that is already inside the container, and it will increase the concentration of the nails. So since chloride is already present here, whatever concentration we're going to have here will add up to this now. Okay, we are now going to rewrite we are going to rewrite the equilibrium concentration or equilibrium expression of this guy. So therefore, I will say PbCl2 giving us Pb2 plus. Now this is x is to x is to 2x. But since we already have chloride here that is common with this guy, the concentration of this chloride based on ratio of 1:1 is 0.05. So I'll now say whatever the concentration of this chloride is, we are going to add the concentration of this guy to this because this is common to this. So we're going to add the concentration of the common ions, right? So this chloride in NaCl has a concentration of 0.05. So I'll now come here. This one we do not know, but whatever the value of this guy is, when we finally know it, it will add up to this guy. So this becomes plus 0.05. That is it. All right, so you can decide not to put this guy. You can still decide to put it. So I'll leave it here. Okay, so I'll now say Ksp will now be Pb2 plus into Cl minus. Now, this explanation but in exams, you don't really have to, put this here. You can just write 2x, but when you want to put the values inside a bracket, you now add the 0.05. Now, this is what I mean. So this becomes, in place of this, you put x. In place of Cl minus, you put 2x plus 0.05 or raised to the power of 2. Now, this is equals to the Ksp, which is 1.6 times 10 raised to the power of minus 5. Okay. So we're going to expand these brackets. You expand the brackets. Now this is x into 2x raised to the power of 2 is 4x squared plus, when you expand these brackets, this becomes 0.2x plus now when you expand these brackets, this is what you're going to get. This is what you're going to get if you expand the brackets. Now do not forget that this x is not going to expand everything here. So this becomes 4x cubed plus 0.2 x squared plus 0.0025 equals to 1.6 times 10 raised to the power of minus 5. So from here now, we'll say Class, you can decide to solve it using, we have in your calculator, we have polynomials with x power being 3. But you can always ignore this for x cubed. So you say, assume for x cubed to be very small. So this now becomes 0.2 x squared plus 0.0025 equals to 1.6 times 10 raised to the power of minus 5. Now when you actually bring this is x. There should be x here as well. There should be x here because this x multiplied everything here. So there should be x here. So when you bring this one to this other side, this becomes 0.2 x squared plus 0.0025 minus 1.6 times 10 raised to the power of minus 5 equals to 0. Now this is now quadratic equation, right? Your a is 0.2, your b equals to 0.0025, and your c is equals to minus 1.6 times 10 to the power of minus 5. Now, if you insert this in your calculator to solve quadratic equation, solving using quadratic equation. So our x now becomes 4.466 times 10 raised to the power of 3. Now for those of us that do not know how to solve quadratic equation using calculator, I'll be actually making a video for that so that you can learn to understand. So therefore, we've gotten our value for x. To now say, recall we had said that x equals to PbCl2. So therefore, molar solubility of PbCl2 is equals to 4.466 times 10 raised to the power of minus 3 molar. And that is the answer to that question. Okay, we have another question here. So first and foremost, what I would like to do here is to first of all get to know the concentration of the common ion. Now we are asked to solve for the molar solubility of MgCO3. So I'll come here and say solution. I want this solving to be much shorter. Now this is the added salt, or what we are dissolving this MgCO3 in. So this is a salt we are dissolving this guy with. So we'll say Na2H8. We're going to have Na plus 2 minus. So this is 1 is to 2 is to 1. So whatever the concentration of this guy is, this is 0.1 molar. So this will be 2 into 0.1, and this will be 0.1. All right, so but if you noticed, it's a CO3 that is common with this is a sparingly soluble salt that was given to us, and this is actually the salt that it was dissolved in. So if you look at two of them, the common ion is basically the CO3. This guy has CO3 and this one has CO3. All right, so we are interested in the CO3. So I'll therefore say concentration of CO3 2 minus is 0.1 molar. So therefore, let's write the equilibrium expression for the sparingly soluble salts. MgCO3 is Mg2 plus. Now, just like we did previously, but I don't just feel like writing it, but I've already done it. You say let the solubility of this, or perhaps you must have done it before now. Let the molar solubility of MgCO3 equals to X. But before we do that, if you look at the mole ratio, this is 1 is to 1 is to 1. So if we say that let the molar solubility of this guy be X, this place will also be X, and this place will also be X. All right. So therefore, in the presence in the presence of 0.1 molar Na2CO3. This will now be X into X. Now when we get to this CO3, remember this CO3 here will add up to this one. So we now have X, plus 0.1. So the concentration of this CO3 in the solution will no longer be just X, to now be X plus 0.1, because this is also in the solution as well with this, because both of them are dissolved in the same container. So now see Ksp of MgCO3 is now Mg2 plus CO3 2 minus equals to, the Ksp is 3.5 times 10 raised to the power of minus 5. Now anywhere you see Mg2 plus, we put X. Anywhere we see CO3 minus, we put X plus 0.1 equals to 3.5 times 10 raised to the power of minus. So this is X times X, X squared plus 0.1X equals to 3.5 times 10. Now when you bring this guy over, this becomes X squared plus 0.1X minus 3. Equals to 0. Now when you solve this using your quadratic equation, now this is my A, this is my B, and this is my C. So when you now solve for your quadratic equation, your X now become please pardon me, this place is not 5, this is my raised to the power of minus 8. So here is actually raised to the power of minus 8. This is minus 8 and this is minus 8, please. This will also be minus 8. So when you now solve for your X now becomes 3.5 times 10 raised to the power of minus 7 molar. So therefore, the molar solubility of MgCO3 in is equals to 3.5 times 10 . Now, you know the interesting fact about this. If you solve for the molar solubility of this MgCO3 when dissolved in water, right? If they had asked you to solve for the molar solubility of MgCO3 in water, or when water is not even mentioned, right? So when water is not mentioned, it is assumed that it is still dissolved in water, right? So if you solve for the molar solubility of this when dissolved in water, the value here will be higher. The value here will be higher. So what does that tell us? It tells us that the molar solubility of a sparingly soluble salt will reduce or decrease in the presence of a salt that has a common ion with itself. Will decrease in the presence of a salt that has a common ion with a sparingly soluble salt. Now, this sparingly soluble salt, MgCO3, was dissolved in sodium carbonate, NaCO3. So there is a common ion between the sparingly soluble salt and the salt that the solution is being dissolved in. All right? There's a common ion between the sparingly soluble salt and this salt here. So because of that, the molar solubility of MgCO3 is going to reduce or decrease. Okay. Please, if you have not subscribed to our channel, make sure you do so by tapping the subscription button. Also, if you have not bought the course package, go to our website www.delzischolarsgroup.com for more details. Thank you.